Recording. So let me start with a quick revision of where we are. We have defined eigenvalues. So let V be an n-dimensional real or complex vector space. A hat V to V a linear map. So look at the characteristic polynomial P hat A hat of T, which is determinant of, is the definition. So K equals R or C depending on the context. So here is the key result. Lambda 0 in K is a root of PAT. That means PA lambda 0 is 0. So this is a polynomial function from K to K. So either it's a real valued function on R or it's a complex valued function on C. And a root is a point of R or C respectively where this function vanishes. If and only if kernel of this operator lambda 0 IV minus A hat is non-zero. So this is the key result. So in other words, you think of it like this. So this is the space. So let's look at suppose K is R to be concrete. Okay. Then, so this is a space of T's. And for every T, and I have a linear map A hat V to V. For every T, I'll have a corresponding map from V to V, namely T times the identity minus A hat. Okay. So this is T. So you can imagine that I have a machine so as I slide this point along the real line, for every point I have a linear map V to V, which is built out of A hat. So the only thing that changes is this part of the linear map. So this part of the linear map does not change, this part changes. So I slide this point along the real line, then the linear map changes like this. Okay. Then for most points in T, this is an isomorphism. One second. For most T in R, TIV minus A hat is an isomorphism, is a bijection. But for some T equal to lambda 0, for some t, this is not an isomorphism. I.e., it has a kernel, it has a non-zero kernel, and these t's, these values of t are precisely the real roots of PAT. So this is the picture. Okay, somebody asked a question. There was a question. Was there a question? Hello? No question.
Sir, I don't think so. It was, I think someone's mic got unmuted accidentally.
Okay. So this is the key result that, in fact, I have proved this in the last lecture. And this is the key result to understand the significance of eigenvalues and eigenvectors and the connection with the roots of the polynomial, of the characteristic polynomial. So let me repeat. So this is a picture you must firmly have in your head. You start with a vector space, finite dimensional vector space, n-dimensional vector space, and a linear map. So A hat is fixed, but then I want a family of linear maps depending on the real numbers, on a real number, which depends on A hat, and that family is for every real number t. I consider this linear map from V to V, and what if you think about what this says? This says that as t goes, as you vary t along the real line, so t is the coordinate along the on the real line. As you vary t along the real line, for most t's values of t, this linear map is an isomorphism. But whenever t coincides with the root of the characteristic polynomial, this linear map has a non-zero kernel, which means it stops being an isomorphism at those points. So that is the content of this thing. Okay. In fact, you can even say more, because if a polynomial of degree n has at most n roots, so it can vanish at most at n different points. So at most there are n points here. If the dimension of V is n, there are at most n points where this happens that the kernel is non-zero. Okay, so in other words, this is the t line. There is lambda 1, lambda 2, lambda n. At most, in fact, lambda m less than or equal to n. And if t is here, TIV minus a hat has no kernel, is an isomorphism. Is an iso. And at these points, these are the roots of PAT. At these points, lambda 1 IV minus a hat has a kernel, is not an isomorphism. So all these guys, lambda MIV minus a hat, all these have non-zero kernels. So let me repeat. Supposing I have a real vector space and a linear map A hat from V to V. If we look at the corresponding, this linear map as a function of t, so at every point here, I have a linear map, namely, so this is t maps to tiv minus a hat. At all these points away from lambda 1 to lambda m, where m is at most n, this linear map is an isomorphism. And at each of the roots of the characteristic polynomial, this linear map fails to be an isomorphism. So, sir, yeah.
Sir, this P of A hat T is equivalent to P of AT.
Yes.
Like, yeah.
Yeah, but A, what is A?
A is a matrix which is corresponding to that linear map.
So is there a definite matrix that corresponds to a linear map?
Yeah, I mean, like we need to define the basis for that.
Yeah, you need to choose a basis, not define. Choose.
Yeah.
Choose. Yeah. Choose. Yeah.
Thank you.
Yeah. Thank you. Yeah. Great. So now, if lambda is one of these guys, if lambda is, if t is equal to lambda 1 or lambda 2 or lambda m, a root of PAT, then kernel of t of lambda I b minus a hat is non-zero, i.e. there exists v lambda not zero such that a hat v lambda I is lambda I. Let me just call this vi. There exists some v for, yeah, not necessarily unique. Okay, and these are called eigenvectors. These are the eigenvectors corresponding to lambda I. So I'm just revising everything that we did in the last class. Okay, and then we proved the following proposition: if lambda 1, lambda k are distinct eigenvalues, and v1, vk are corresponding eigenvectors, then these are linearly independent. Corollary: if a hat is such that PA hat has n distinct roots, there exists a basis of eigenvectors of A hat. So there exists a basis of V consisting of eigenvectors. Yeah, so this is more or less what we did in the last lecture, and today we are just going to do examples. But there's a lot to unpack in the examples.
Hello, sir.
Yes.
Sir, in the last two propositions that you gave in the class, in the previous class at the end. So in the second proposition in the notes, there is a point that the subspace generated.
No, I don't want to deal with that today. Let's postpone that.
Oh, okay, sir.
Yeah. But did you try to read it and you have a doubt?
Yes, sir.
Okay, very good. So I'd rather leave this for you to figure out. But if there's a doubt, you tell me. What's the doubt?
Sir, I mean, there is a point that if lambda 1 to lambda L are some distinct eigenvalues,
Yes.
and V prime is the subspace generated by the span of these,
Right.
then that V prime is actually invariant under the linear map that we give from V to V. This is written in the notes. I did not get that point actually.
Yeah. Oh, you don't get why it is invariant.
Yes, sir.
So the point is each of the V lambda i's is invariant. Did you get that?
No,
So
sir.
fix. Okay. So this is an important point. So I will answer this. Okay. So everybody pay attention. Let lambda 0 be a root by an eigenvalue of a hat. So this means kernel lambda 0 IV minus a hat is not equal to 0V. And this is what? This consists of V in V such that lambda 0 IV minus a hat V is 0, but that is the same thing as V in V such that a hat V is lambda 0 V. And this is what we've defined as V lambda 0. Okay, I'm just taking the definition of V lambda 0 and sort of putting it in context. So far I have not addressed your question. By the way, who was this who asked the question?
Sir, this is Nilabcho.
Okay, so I've just I have not begun to answer your question. I just want to explain that V lambda 0, the set of eigenvectors corresponding to lambda 0, and you add the origin to it, so it's a subspace, and that's just the kernel of this linear map. So does everybody agree with this? So this is the definition of V lambda 0. And I've just said that the definition of V lambda 0 is equivalent to saying it's the kernel of this linear map. Does everybody agree with this?
Yes, sir.
Yeah. So now, so lemma, this partially answers your question. V lambda 0 is invariant under a hat, i.e., if a vector V belongs to V lambda 0, so does if then AVV also belongs to V lambda 0. Proof. So V lambda, sorry. So let W equals AB. So this is a definition of W. We need to show AW is equal to lambda 0 W, right? That is what the lemma says. But AW is A of AB, which is I keep forgetting, hats everywhere. A hat of lambda V, which is lambda of A hat V, which is lambda of W. So that's a proof of the lemma. Satisfied?
Yes, sir.
Yeah. Now, if to show that the subspace generated by the eigenvectors, it's clear, right? You take any vector which is a sum of some eigenvectors, maybe corresponding to different eigenvalues. Apply A to that sum, then component-wise, each of them will be will still lie in the corresponding eigenspace. That's all.
Okay, sir. So invariant under linear map means, I mean, I was thinking that if two different linear maps are there, then if lambda not belongs
No,
to
no,
one
no.
of them.
Invariant under a linear map. So it means that if I take a vector in that subspace and act on take any vector in that subspace, act on it by the linear map. The resulting vector also belongs to that subspace. That's what it means.
Okay, sir. Understood. Thank you, sir.
Yeah, yeah. Okay, yeah. So thanks for this clarification. Can you just send me a mail asking me to make this explicit in the notes? What does invariant under a linear map mean? You are not the first.
Yes, sir.
This is not the first time people have asked this question. I should clarify it in the notes. Just send me a mail.
Yes, sir. Surely I'll send them.
Yeah, thank you. Very good. So let us now look at examples. Examples. If V is one-dimensional, then and A is a linear map V to V, then A hat is of the form A hat B is equal to AV for some A. So there exists a scalar A for all V. Then i.e., any linear map V to V is of the form A times IV for some scalar A. So these are the only linear maps from a one-dimensional vector space to itself, namely scalar multiples of the identity. So then, so PAT is T minus A, and PA hat T is T minus A, and V equals BA. Okay, where BA is eigenspace corresponding to the eigenvalue A. So there's the whole vector space consists of only one, there's only one eigenvalue, namely the scalar corresponding to A hat, and the whole vector space is just that eigenspace. That's all. So now, to let V equals n cross 1, column vectors of length n. Let lambda 1, lambda r be distinct scalars. So here K can be R or C for this example too. So R is less than or equal to N. Let Mi greater than or equal to 1 be integers M1 to Mr such that M1 plus M2 plus Mn equal to N. Let AI be the Mi cross Mi matrix. Lambda I, lambda I, lambda I, Mi cross Mi. In other words, this is lambda I times the identity matrix of size Mi. Let A be the n cross n matrix. A1, A2, A3, AR, like this. Zero everywhere. Then PAT is product I equal to 1 to R, T minus lambda I to the Mi. And let's see what happens to A at acting on. So now I'm going to ask you a question. Okay, now I've gone very fast. Now the question is, this is equal to what? So take 5 minutes. I want everybody to take 5 minutes, take a piece of paper and figure out what should, some of you probably see the answer now. And actually, if you look at my notes, you can figure out the answer. But I really ask you not to look at the notes. Take 5 minutes, take a piece of paper and figure out what the answer should be from here. So
Ask a question.
So there is a question. What is the question?
In your n cross n matrix with A, it's n cross n, but your last element is AR. I'm not sure why.
This is AR. One
It
second.
should be AN because there's n rows and n columns.
No. There are only R matrices. There is a. We are looking at. We are trying to construct n cross n matrices, but the matrix will be in blocks of size Mi cross Mi, diagonal blocks, and there are only R of them because there are R blocks, there are R scalars, and
Okay.
yeah.
Right.
Yeah. So this is a M1 cross M1. This is M2 cross M2, and this is MR cross MR. And since the sum of the Mi is equal to N, this is MR. Yeah, is equal to N. This matrix A that I have constructed is indeed N cross N. So the question is what if I act on the so this is the standard, one of the standard basis vectors of column vectors. This is what I would call EJ. So question is, what is AEJ?
Sir,
Yes.
sir, can two non-similar matrices have same characteristic equation?
Yes. Yeah, that's a very good question, and in fact, hopefully we'll get down to it today.
Okay, sir.
Yeah, but I want you to, yeah, that's a good question. Yeah. So I want you to think about what is AEJ. AEJ is going to be a column vector. What you have suggested is a matrix. And I'm asking, replying to Ishan. Ishan, A sub j is a MJ cross MJ matrix. Somnath and Rajagopalan, it is not, see, A is, I'm acting on a column vector, I'm multiplying a column vector of size n with a matrix on the left, n cross n matrix. The result should be a column vector. Yes, yes, that is yes, yeah, I think many of you are yeah. There is, Romit, there is no better way to define it, I think. Yeah. Okay, so some of you had time to think about it, and the answer is there in the notes. So in fact, I will give the answer to a slightly different question. So I will just say, give the answer. The eigenvalues of A are lambda 1 to lambda r P A T. So by the way, A is A hat. So A gives a linear map A hat. So its eigenvalues are lambda 1 to lambda r. P A hat T, which Shakti never always reminds me, is by definition P of A hat, P of A. It is product I equal to 1 to r, T minus lambda I to the mi. So what is the eigenspace V lambda I? This consists of vectors with all entries 0 except in a certain stretch. And what is this stretch? This is the this is the stretch consisting of rows j which are less than greater than m1 to plus mi minus 1 and less than or equal to m1 mi. Okay. So this range is like this. Okay. So this is the answer. I want you to read the notes and convince yourselves that this is the case. Okay. So now let us yeah. Now let's consider the question. Suppose dim v is greater than 1, so call this n, and PAT has only one root. It is of the form t minus lambda to the n. What can you say about the linear map? Okay, so what can you say about A hat?
Diagonal elements.
Sorry?
Equal diagonal elements.
So this is a good guess. So by the way, so again you are confusing the matrix with the linear map. But what you are saying is so example of such a hat is lambda times IV. And your question is this the only example? Okay, so in fact, somebody asked, are there if two matrices have the same characteristic polynomial, are they similar? Okay, so this is related to that question. So if n equal to 1, we have already seen this is the only example. Yes. But n equal to 2, okay, so let us see. So so now I'm asking a very, very simple and concrete question. So if your mind is full of confusion, get rid of all of it. We are asking a very, very simple question. Okay, and by the way, many of you might prefer that I formulate this question in terms of matrices, because I know that you have a resistance to thinking of a vector space without a basis. But believe me, for this, it's much simpler if you don't think in terms of matrices, but think of linear maps. So let A hat V to V be a linear map. So dim V is 2, and suppose P A hat T is T minus lambda squared. Okay, let us see. So what can one say about A hat? Well, we know one thing. We know kernel of TIV minus A hat, lambda IV minus A hat is non-zero, right? right? Because P, if I substitute T equal to lambda, the characteristic polynomial vanishes. So there is, the kernel is non-zero. So there are, so what are the possibilities? I have V is two-dimensional. There is the zero subspace, and then there is the kernel of lambda IV minus A hat, which is a subspace. So now this is non-zero, so this is not equal. So this is a non-zero subspace. So what are the possibilities for the dimension?
1 or 2.
Dimension is 1 or 2, right? Because the dimension here is 2, and this is a subspace that's not the zero dimensional, not just, it's not the zero subspace. So the dimension has to be at least 1. So if it's 2, if dimension is 2, what does that mean?
The kernel is V.
It's all of everything. It's kernel is everything. A hat is actually V. This implies that A hat V equal to lambda V for every V, and this means that A hat is, as in the original guess, is indeed lambda times the identity. Okay, but what if dimension is 1? Is this possible? So now, again, I want you to take a break and try to see what the possibilities are. Is this possible that you have the characteristic polynomial is T minus is lambda, T minus lambda squared, but the dimension of the kernel is, but the eigenspace corresponding to lambda is only one dimensional. So you can look at the notes, but try to fool around on a piece of paper and pencil, and I'll give you 5 minutes. And anyway, I think, yeah, I might as well take a break now, and we will come back. V1 such that A hat V1 is lambda V1. Okay. Now, so dimension of V is 2, so we can find a V2 such that V1, V2, take any vector that's linearly independent of V1, and that will give you a second vector, so that together they form a basis. So that is a basis. So then we have A hat V1 is lambda V1, and A hat V2, well, it's some vector in V, okay? So it will have to be of the form A V2 plus B V1, right? Because any vector in V is a linear combination of V1 and V2. Okay, so now if you write the base, so write the matrix of A hat with respect to the basis V1, V2, and we find A is lambda A B 0. But then PAT is T minus lambda T minus A. And for this to be equal to, T minus lambda squared, we need A to be equal to lambda. So we have, in fact, A hat V1 is lambda V1, and A hat V2 is lambda V2 plus some B V1 for some B. Okay, so so now exercise the necessary and sufficient condition for dim of lambda IV minus A hat to be equal to 1 is B is non-zero. This scalar B should be non-zero. Now, so this is an exercise. Now, exercise again. This is all very well explained in the notes, so which is why I'm going so fast. Exercise by if B is non-zero, we can in fact choose B1 and B2 such that A is actually of this form. So this is an example. So in other words, you can actually choose eigenvector, an eigenvector V1 and then another vector V2 such that the matrix of your given linear map A hat with respect to this basis is of this very special form lambda, lambda, and 1 here. Okay. So this is an example of what's called a Jordan canonical form. Which we will study later. We will study in general later. Okay, so already you can, so I hope this answers the question that was raised before. The characteristic polynomial does not determine the matrix up to similarity because so remark, the matrices lambda, lambda, 0, 0, and lambda, lambda, 1, 0, both have characteristic polynomials t minus lambda squared.
There is a Jordan.
1 second, they are not similar. Yeah, sorry, somebody said something.
There is a Jordan canonical form covered in the notes.
It is covered in the notes later. Yeah, it is covered in the notes.
Okay. Yeah.
Yeah. I don't recall it to what, how much I spent time on it, but it is covered. Yeah. Yeah. So, so again, so this 2 by 2 case is very, very important for you to understand. And so, but again, strip away everything that went before and everything that's going to come later, but just look at this remark. So this is a very, very important remark to understand. First of all, so all I have done is put before you two 2 by 2 matrices. One is lambda times the identity, and the other is is of this form, lambda lambda 1 0, and you can check directly by hand by computing the determinant that t minus both these are the same characteristic polynomials, t minus lambda squared, but they are not similar. Why? Because the only matrix similar to lambda times the identity matrix is itself, because every matrix commutes with lambda times the identity. So these two are not similar. So this answers the question in the negative. If two matrices have the same characteristic polynomial, are they similar? No. And this is a very, very important phenomenon.
Okay.
In the notes, I then go on to ask what happens if n is 3, and then we classify. So the question is if dim b is so this dim b is 3 and PAT is t minus lambda to the cube, what can one say?
The similarity was established as the equivalence relation, right?
It is an equivalence relation, but what does that have to do with this? Yeah.
I mean, here lambda, I mean, the first matrix should be similar to matrices of this class only.
Yeah, right. Yeah. All I'm saying is that this matrix is only similar to this. This matrices of this class, the equivalence classes contain only that matrix. So it cannot contain the second matrix. The similarity, the equivalence classes of matrices of this kind are singletons.
Yes.
Sir,
yeah.
Sir, if two matrices in the Jordan canonical form is different, then
I don't want to talk about Jordan canonical forms now. Yeah.
Okay, sir.
Yeah, it will get. I mean, there are. Let's go step by step.
If the diagonal elements are all same for two matrices in Jordan, like if they are the characteristic. Yes, no, I got it, sir.
Yeah. So so this is an exercise. If dim b is 3 and PAT is t minus lambda cube, what can one say? So this is exercise 4. This is example 4 in the which is in my notes, which is entirely an exercise. Okay. Then 5 for theta in the range 2 pi 0. Consider the 2 by 2 matrix A theta, which is cos theta minus sin theta, cos theta. So if you look at its action on R2, what it does is to take a vector in take any vector v and turn it around by an angle theta. PA theta t is t squared minus 2 cos theta plus 1. Since 4 cos squared theta minus 4 is less than or equal to 0 unless theta is
less than equal to.
Wait. Less than or equal to 0. Less than 0 unless theta is cos theta is plus minus 1. This has no real roots. unless cos theta is plus minus 1.
It should be 2 cos theta t.
No, I'm just looking at the, thank you, 2 cos theta t. Thank you. In my notes also, it should be that. Yeah. So this corresponds to the fact that geometrically you see that this linear map from R2 to R2, the only time it has an eigenvector is if it's the identity or minus the identity. Corresponds to the fact, to the geometric fact that the linear map A hat theta has no eigenvectors unless theta is 0 or pi. Very good. But now I can consider the same matrix, A theta, but consider the corresponding linear map C2 to C2. Okay. So Z1, Z2 maps to A hat Z1, Z2, which is A Z1, Z2. Matrix multiplication. Here's matrix multiplication. So now, what are the eigenvalues of this map? This map are the roots of the same polynomial, but now I am allowed to look at complex roots. Which are e to the plus minus I theta. Okay. And we get eigenvectors 1 plus minus I equals e to the I plus minus I theta 1. So if theta is not 0 or pi, it has two distinct roots, complex roots, e to the plus minus I theta. And there are corresponding eigenvectors which do form a basis of C2. So the vectors 1 plus minus, I have to be a bit careful here. Yeah. No. Yeah. So the situation is clear. Once I am allowed to think of an n by n matrix as a linear map from complex vector space Cn to complex vector space Cn, then every root, there are as many roots, maybe counting multiplicities as the dimension, and every root corresponds to an eigenvector. So, but the same matrix considered as a linear map from R2 to R2 may or may not have eigenvectors, because the characteristic polynomial may or may not have real roots.
Sir.
Yeah.
I had a question.
So 1 second. I'm
Yes,
going to stop the recording and then